All right, gonna do a video saying what is the tensor algebra. Gonna go from tensor algebra, and then later I'm gonna show what the exterior algebra is, and then the Clifford or geometric algebra, and show how there's sort of a common flow where you've got a vector space. You want to figure out how to multiply stuff. So usually what you then do is you go to the most general way to multiply, and then to get the things that are more interesting usually is, well, there's some other constraints you want to put in. So then we after we go to this biggest algebra, the tensor algebra, then we quotient out to get, say, the exterior algebra, or then ultimately, if we've got a quadratic form, we go down to the Clifford or the geometric algebra. Okay, so with that in mind, yeah, motivation, which I was just starting to say, and I'll show. I think this video I'll talk about so just quickly what it is, and then next video I'll actually construct it and show it has the properties that we want, and then I'll repeat for the exterior and the Clifford. So let's say we got a vector space. All right, well, we can add vectors and we can scale them. That's pretty lovely. There's all sorts of reasons, though, why we might want to figure out how can we multiply them. So I won't maybe give motivation for why you might want to, but let's just assume we're trying to figure out how we might multiply vectors. So, well, vector spaces equipped with a multiplication, that's what algebras are, at least in this context. So what we want is some sort of algebra generated by a vector space. All right, so to be clear, though, we want a universal one. So first off, it's good just to say, let's assume we want a unital and associative algebra. Associative because we pretty much always want our operations, our products, and our sums to be associative. Not always, but the vast majority of the time we want them to be associative. And unital, it's useful to have a unit, an identity for multiplication. So we're looking for a unital and associative algebra. If I don't say that anymore, just assume our algebras here are unital and associative. To be clear, there are lots of algebras you can embed a vector space into. And actually, I shouldn't use the word embed. Well, yeah, we basically want to embed, but do a linear map from the vector space into the algebra. So let's be clear on the problem we actually want to solve and what its universal formulation is. So my phone won't ring during them. So given a vector space B, we want a unital and associative algebra, and I'm just going to go right to calling it T of V. It's going to be the solution. So this is just the notation for the tensor algebra generated from V. So we want T of V with a linear map that goes from V into T of V, and such that it satisfies the following condition. For all other unital associative algebras A and linear maps from V into A, we want to have a diagram like this. So let's be careful about this diagram. This is a linear map from the vector space into the tensor algebra. Linear, so we're looking at the algebra as a vector space here. So I'm using T for both because it's a functorial construction, unless I'm forgetting facts entirely, but I'm pretty sure it's functorial, so I'll just use the same letter for both the effect on objects and the map. And then let's do a linear map from V into some other unital associative algebra. The point is that we get a unique then map from the tensor algebra into any other such algebra. So anytime we embed a vector, or anytime we map from a vector space into some unital associative algebra with a linear map, we always can factor through the tensor algebra to get there. And that's what we're going to do in a minute in a few videos when we do the exterior or the Clifford algebra. Just to be clear, then we end up having a category, and the tensor algebra ends up being initial in that category. So in the category, the objects, so T of V, and then this map from V into T of V, it's initial in a category where the objects are unital associative algebras equipped with linear maps from the underlying vector space into the algebra. So these two, the algebra plus the linear map from the vector space into the algebra, this is the object. And then the morphisms, so this would be one object here. Here's our algebra, here's our linear map. This would be a different one. Here's our algebra, here's our linear map. Then the morphisms would be things like this F that map from here to here. So the point is that the tensor algebra, what we're after is an initial one. And that makes sense that would be, there's a good reason why that's the one we want, because that one captures what we're after. It's the, I think I actually say this on the next slide. Yeah, so I say here, it's the initial object in this category. It's going to be the algebra that's has the least constrained. It's the least constrained algebra that we can put our vector space into. So what is the tensor algebra? Well, the not satisfying answer is it's the solution to that universal problem. And it is unique up to unique isomorphism. So it essentially, there is only one such thing. It's not even just unique up to isomorphism, it's up to unique isomorphism. Now, as to what it is, well, next video I'll construct it, but let me just tell you, what it ends up being. This kind of tells you how to construct it anyway. So T of V ends up being a formal sum, and it's a graded, so it ends up being a graded algebra. And so it's a formal sum where the zeroth order term is just the field. So this is the actual underlying field from the vector space. Direct sum with the vector space, direct sum. And then here we've got the tensor product. So it's an X with the circle around it. Same as the direct sum with a plus sign. This is now the circle with the X. So it's V tensor V plus, and then V tensor V tensor V, and so on. So if you want to, you could just write it as an infinite sum, I suppose, where then this V and this is up in the exponent K. We define the zeroth one to be the field, and the nth term is just these, it's these formal products of n elements in the vector space. So that's, as I'm saying here, this is basically just a formal product. It is a free construction. So it's just like if you've ever done free groups or something where it's like you're literally just putting the things next to each other. That is what we're doing here. So just as I don't know if it's actually that informative, but just to be clear as an example, if we have two vectors v and w, you can take their product and you just write it v tensor w. So in general, a general tensor is a formal sum of forms, and so like this is just one example of a general tensor. So there's a zeroth order term here. It would be 0 on the first order term. There's a second order term and a third order term. So terms all of the same order. This is an elementary tensor. This is an elementary tensor. This is an elementary tensor. All of them added together, that's no longer an elementary tensor. I guess I should say it's finite sum. So there's no infinite tensors in the algebra. Although I guess you can equip analytic structure and then start talking about analysis in them. But all right, let's close up. So usually it turns out, well, more or less, the tensor algebra is usually too big. And the point is, we wanted the algebra that we could embed our vector space into. We want to get a vector multiplication with the fewest constraints. Well, the reason it's too big is usually we care about some constraints. Typically, geometry is what we care about. Not always, but often it's a geometric concern. And so then what happens is, well, we then, instead of having this most general one, we put on some constraints. And so then we end up usually with this sort of picture, which is actually, we go from V into the tensor algebra. Like, great, we can now multiply vectors, but it's too big, it doesn't incorporate useful constraints. So then what we do is we map from this into a quotient space. So we usually we'll define some sort of equivalence relation, and we're going to quotient out by the useful constraints, which come from geometry usually. And that's exactly what's going to happen for both the exterior algebra and the Clifford algebra. So next video, I will just construct T of V, though I've kind of already said what it is. And the point is then to construct it and prove it actually has the properties that it's initial, that we have a linear map, and that it's initial in that category I talked about. And then from there, we'll go to the exterior algebra and the Clifford algebra. I hope people find this useful.